I think algorithm is very popular and widely used in our daily life to protect our data or shift bank card or something. So I think so. Also, because of his work in the public key cryptography, Professor Shamir is also got the Turing Award in 2002 for the engineer's contribution for making public key cryptography useful in practice. In addition to the Turing Award last week, yeah, Professor Shamir also got the Wolf Prize in mathematics for fundamental contribution to mathematical cryptography. So, Professor Shamir, just born in the 1952, is a professor in the Department of Computer Science Department, Weizmann Institute of Science. He is one of the most senior computer scientists globally and a top expert in the field of information encryption and decryption. Recently, as a development of artificial intelligence and its wider application, Professor Shamir also distracted his attention to the artificial intelligence to the security of artificial intelligence. So today he will give us a talk on the polynomial time cryptanalytic extraction of neutral network model. Let's welcome.
Good afternoon, everyone. Can you hear me? Yes. So it's my pleasure to be here for a second time at ICBS and to address you. I'm, of course, in the last few years, I've been following NDR's advice that all computer scientists should become machine learning experts. So I've started looking into areas which are in between security and machine learning. And there are many, many open problems and interesting challenges there. And I'm going to describe today my latest research, which had just been presented a month ago at Eurocrypt 24. And this is joint work with a large group of collaborators who are from the United Arab Emirates. And this is a first, because I think that so far there have been no joint papers between Israeli scientists and United Arab Emirates scientists. But this dream had become possible after Israel signed the peace agreement with the UAE. So I'm not going to reveal any secrets here if I tell you that companies are spending billions of dollars in order to train deep neural networks in order to achieve all kinds of tasks. And after companies spend so much money on the training, in many cases, they do not reveal the model that they trained. So you have no access to the parameters inside the deep neural network, but you are allowed to access the deep neural network as a black box. You can give it an input, and then you get an output. Then you can give it another input, and you get an output. And the question that I'm going to ask in this talk is whether this practice of allowing people to interact with a black box representing a deep neural network is dangerous or not dangerous, in the sense of whether an adversary can extract all the parameters from the network or not. Okay, so for those few of you who haven't seen deep neural networks, I'll give a very short introduction. Deep neural networks are mostly linear. They have linear functions. The only nonlinear element is the simplest possible nonlinearity, piecewise linearity, which is called the ReLU function, rectified linear unit. And this function is a function from one real valued input to one real valued output. If the input was negative, the output is 0. And if the input is positive, the output is the same as the input. So it just bends the line, and this is the only source of nonlinearity in the whole network. Then, in order to build a deep neural network, and here I'm going to talk only about the simplest model of deep neural networks, we can we can solve the problem with more complicated deep neural networks, but for the sake of simplicity, I'll concentrate on fully connected, forward-only connections. So you have a bunch of inputs which are, each one of which is a real value, a number from -infinity to +infinity. Then you have an affine mapping, or a linear mapping, plus some constant term, which makes it affine and not linear. And this mixes together. And so there is some mixing together here, some mixing together here, linear mixing. And then the output of each one of those linear affine mappings is used as an input to a ReLU. And then you get only a collection of non-negative values coming out of the first layer. And then you have another affine layer, which again mixes everything together. You go through a ReLU layer, and you have a certain number of layers, and you get eventually a vector of numbers, not necessarily the same dimension as the input, but each one of those values is a real number. And for example, if you wanted to use the deep neural network, as a classifier, then you are going to associate this number with the probability that the input image was a cat, and this is the probability that the input image was a dog, and this is that it was an airplane, and so on and so on. And your classification is the highest number in this vector of probabilities. Any questions about how deep neural networks look like? I think that you all know this. So deep neural networks are defined by their structure. The depths are how many layers there are, the width di of each layer, how many neurons, how many ReLUs are in each one of the layers, and by the weights, which are all the coefficients and biases. The coefficients are what you multiply each input by, and the bias is the free term that you are adding to the whole linear mapping. And a question I'm going to pose is, how difficult is it to extract or interpolate or steal, you can think about it any way you want, all the internal weights of a deep neural network when you are given this neural network as a black box, and you can freely interact with it. So there are basically two questions. Whenever you deal with complexity, you decide what are the measures. So sometimes you ask about time and space, and in this case, I'm interested in how many queries you are going to ask, and then how long it's going to be to utilize the answers you got in order to extract all the weights. And the model is one in which you are allowed to ask questions adaptively. So it is, you choose the first query, you get the answer. Based on the answer, you are allowed to choose the next query, and then you get the answer for the second query. And then you can again, in an adaptive way, choose your queries. So these are the two measures we are going to talk about. More mathematically, the problem is the following. You choose the input, you evaluate the black box function DNN, deep neural network, and you get the first output V1. It's a vector of real numbers. Then you choose another input x2, evaluate the function, and get a second vector V2, up to VQ if Q is the number of queries. And notice that these are systems of equations, nonlinear equations. And the reason that they are nonlinear is twofold. First of all, there are the ReLUs there. And the second is that actually it's not a system of equations in which I'm trying to solve for xi. Xi are the queries that you used, so they are actually known. What I'm trying to solve is for the internal parameters, the coefficients and the biases inside the deep neural network. So the xi's and vi's are known, actually chosen by the attacker, and the internal parameters is what you are trying to solve for. So how difficult is it to solve a system of equations over a deep neural network whose source of nonlinearity is the ReLU? And even though the ReLU by itself is very simple, once you get into deep neural network with many layers, the mapping from input to output becomes mind-bogglingly difficult. It's very, very difficult to write down and to understand exactly what is the relationship between the input image and the decision whether it decides that it's a cat or a dog or a horse or an airplane. Okay. Now, this problem is not new. It had been researched for more than 30 years. And it's interesting that one of the first few results came from a cryptographer, Ron Rivest, who together with his student Avram Blum, now a well-known expert in machine learning, they showed the first result, the first complexity result about the problem. And they showed that something very similar to what I stated is NP complete, which means that you have no chance of getting a fully polynomial time algorithm unless P equals NP. But their model was different, not the problem that I told you, because their model was when the inputs and the outputs are chosen by someone, given to the attacker. He's not allowed to ask his own questions. He's not allowed to work adaptively. He's given pairs of input-output, and in this model, you can encode some NP-complete problem by very carefully choosing what are the inputs and what are the outputs. So basically, you express subset sum problem in this way. And in this complexity result, the model was also very, very restricted. So the question, which was shown to be NP-complete, is that can there be a very simple 3-neuron, 2-layer network? Only this structure is allowed, not any bigger one, which, when given a particular input, provides a particular output. So you see that it's not exactly the problem that I presented. And also, because in 1993, when the result was shown, ReLU did not exist. So actually, they used something which makes it simpler to encode binary decision problems, namely, they used the sign function. If the input was negative, instead of ReLU, the output was always -1, and if the input was positive, the result was always +1. But this was not the big issue. Any questions about this early result? It doesn't solve our problem, but it's interesting. Next development happened a year later when a very famous mathematician, Charles Fefferman, who got the Fields Medal and he got the Wolf Prize, and he's a very good analyst. He published a paper from a mathematical point of view about reconstructing a neural network from its outputs. And there, he again considered a different problem. He was not interested at all in complexity theory, how difficult it is. Instead, he asked the question, if I gave you all possible input-output pairs of a deep neural network, does it uniquely define the internal structure, the internal parameters of the network? And he analyzed very carefully the problem, and he showed that given the complete input-output relation, then the network is uniquely determined up to certain internal symmetries, which I'm not going to describe exactly. So he characterized exactly to what extent the parameters of a network are defined by the full input-output behavior. And the answer was that more or less it is uniquely defined, so we have hope of extracting the parameters by looking at input-output. But he didn't say if it's polynomial number of queries, exponential number, how long it takes to process them, etc. And one more thing that characterized his result is that, again, ReLU didn't exist in 1994, so he was actually looking at the activation function, which is not sine, but a sigmoid. A sigmoid starts at 0, and then slowly increases towards 1, and then it stabilizes at 1. So it's a continuous differentiable function, and used tools from analysis in order to show his result. We are talking about ReLU, which is very different nonlinearity. Then there were dozens of additional papers that I'm not going to describe. And the best result, previous result, before our result, was the following paper. No, this is still about Charles Fefferman. So he proved that for sigmoid-based DNN, all the weights are uniquely determined by the network's full input-output behavior up to certain symmetries. So the best previous result was published at Crypto 2020, and it's interesting that again, cryptographers are involved in this. And Carlini, who is one of the best known researchers dealing with security of deep neural networks, he published many important papers about adversarial attacks. And he showed that many attempts, for example, to immunize a deep neural network against adversarial attacks will actually fail. And together with Jagielski and Mironov, they presented an algorithm which extracted all the weights from the network, but it required a polynomial number of queries and exponential amount of time to process the answers. So there was something that he couldn't determine there, so he needed exhaustive search over a certain space of possibilities, and therefore his running time was exponential, but the improvement, the reason that this was an important paper, was that he showed that number of queries you need is only polynomial, and whenever I say polynomial or exponential, it's a function of the number of neurons in the network. Okay, so for their attack, to complete it, there was one step which required exponential amount of time. They had to exhaustively go over all the possible combinations of signs. So basically you had to guess whether ReLUs are on their negative side or on their positive side. This is something you didn't know. But once you know which ReLUs are on the positive side, which ReLUs are on the negative side at a particular point in the input space, then the system becomes much easier to solve because you don't have the nonlinearity. You either replace the output by 0 or you replace the output by the input, and therefore, after such guessing, the problem becomes much easier. This ends the historical part, the background you need to know about what was known about the problem of extracting weights from interacting with deep neural networks. Any questions? Yes. Excellent question. In our paper, we make the assumption that we know the architecture. In reality, we don't need it. We have expanded techniques that will determine the architecture, how many layers and how many neurons per layer is part of our attack. But I'm going to describe to you the simplest version just to make life, to make the talk more understandable. Other questions? Yes. Yes, I can attack ReLU. I can attack several other types of activations. For example, something called leaky ReLU is also going to work. I cannot attack the sigmoid function. Sigmoid function is too difficult. For a reason you'll see in a moment. Every piecewise linear I can break. Okay. Other? Yes. I cannot hear you. No, the attack works for many, many other architectures. I'm going, in my talk, to concentrate on plain vanilla networks, feed forward, fully connected, even fixed number of neurons in each layer. I just make all the possible simplifying assumptions to make the explanation easier, but it's not really needed for the attack. Okay. So, the paper by Carlini, Jagielski, and Mironov included some examples showing that they could really extract all the parameters, but due to the exponential running time, they could only demonstrate their attack on toy examples where after the first layer, which is easy to extract, all the later layers contained up to 20 neurons, and they showed it for maybe a 3 or 4 layer network with up to 20 neurons, because 2 to the 20 is 1,000,000, and then they could handle it, even though it was exponential time. Okay, our new result, I will show how to extract all the weights and the signs using polynomial number of queries and a polynomial number of amount of time. And our attack follows Carlini et al. Techniques, but add several new ideas that they missed, which completes the attack, polynomial time attack. And many of the ideas that we are adding are coming from differential cryptanalysis. And this looks strange because what's the connection between deep neural networks and block ciphers against which differential cryptanalysis was developed? So I'm going to explain it in the next slide, but I just want to mention that it's not only a theoretical attack. We took real life example. For example, we took a network with 8 layers, 256 neurons in each one of the 8 layers. So it has about 1.2 million parameters. And we found everything we needed in 30 minutes on a powerful computer, which is available in the United Arab Emirates, but not at the Weizmann Institute. So you need a good computer, but then you can solve it in a practical way, even real life examples. And the original attack would have required 2 to the 256, totally impossible, and the new one, 30 minutes. So I said already, I assume that deep neural networks are ReLU-based, fully connected, known architecture. We assume that the inputs and outputs are real numbers with unbounded precision, and that doing arithmetic operation over real numbers takes unit time. You can take 2 infinitely precise numbers, add them, subtract them, multiply, divide in unit of time. In reality, in our demonstrated attack, we use 64-bit numbers, so we don't need infinite precision. The reason I'm going to make the assumption here is just so I'll not have to worry about errors and error propagation, etc. I'm going to assume that every calculation I'm making is absolutely precise. But that's only to simplify. When you actually attack the network, you use 64-bit arithmetic, or depending on the depth. Okay. Next. This should convince you that there are some close relationship between the problem of extracting the weights from deep neural network and block cipher cryptanalysis. So here you see the deep neural networks that I mentioned before. And for those of you who haven't seen it, this is an example how AES, Advanced Encryption Standard, looks like. So here, instead of having real valued inputs, you have a bunch of bits. Each entry is a single bit. And then you are mixing linearly, or even affinely, all those bits. Here, each one of those outputs is 8-bit quantity, which is fed into some nonlinear function which we call substitution box or S box. And then it maps 8-bit input in a nonlinear way into 8-bit output, and 8-bit from here, 8-bit from here, 8-bit from here, etc. are again linearly mixed and go through a substitution layer until you get a vector of bits, and this is the encrypted result. On the left side you have the plain text, and here you have the ciphertext. If you look at it, it's exactly this. It's exactly the same problem, because you have a vector of inputs in both cases. You have alternating layers of linear, nonlinear, linear, nonlinear. All the nonlinearities are actually known functions. ReLU, everyone knows how ReLU operates. In S boxes, everyone knows the definition of the S box. It's published by the designer of the cryptosystem. Where is the secret? In block ciphers, the secret is a subkey that you are exclusive ORing into this linear mapping. So it's part of the linear mapping that you don't know and you're trying to extract. And here, the unknowns in this problem are the weights and biases in the linear function. So it looks almost the same. Yes? I cannot hear. There's some vibration in the room. there are going to be a lot of smoothness assumptions in the deep neural network. You'll see it later. Here it's discrete world, and here it's continuous world, and that's the main difference between the two. Any questions about this similarity? And because there is this similarity, techniques from the best algorithm we have, how to break block ciphers, which is differential cryptanalysis, can be used in order to attack deep neural network and extract their secrets. Okay, I already said all of this. Now we talk a little bit about symmetries. We have no hope of uniquely determining the parameters of a deep neural network because there are internal symmetries. You can change some of the parameters without affecting the input-output behavior at all. For example, if you change the order, internal order of neurons in the first layer, you just adjust the coefficients in the next layer to follow the correct value in the previous layer, and the network will behave exactly the same. But formally, if you look at the weights, the first neuron will look different, but it just moved to a different location in the first layer. So exchanging orders is a symmetry which does not change input-output behavior, so I have no chance of finding the correct, the original order of the neurons. Similarly, if there are two neurons which have exactly the same vector of inputs, the same vector of coefficients, I can combine the two neurons into one new neuron by linearity. So there are all kinds of small things like this, but there's one linearity, one kind of symmetry which I want to emphasize because it will be important in the rest of the talk, and this is related to the fact that ReLUs are nonlinear, but there is a remnant of linearity there. Namely, it is positively, multiplicatively linear. What do I mean by that? If this is a kind of two-neuron neural network, I could take this linear mapping and I can change simultaneously all the coefficients here by multiplying all of them, for example, by 5. So suppose that I multiply all the coefficients by 5, also the free term is multiplied by 5. Not only the coefficients of the inputs, but also the free term is multiplied by the same constant. So what will happen? The output of this linear mixing will increase by exactly 5 if all the inputs, all the coefficients are multiplied by 5. What happens when I take the ReLU and multiply its input by 5? If the input was negative, it was 0, remains 0. 0 is 5 times 0. If it was positive, then I multiply the input by 5, the output is multiplied by 5, and therefore the multiplicativity by 5 passes through this nonlinearity. So it is a little bit linear with respect to multiplying by a positive constant, but remember that in order to compensate for the fact that here all the coefficients were increased by 5, the output was multiplied by 5. So in the next layer, every neuron should divide its coefficient, how it is using this value, it should multiply by 1/5. And then the output of the next layer will go back to the same as the originally. So I can increase parameters in one layer and compensate by changing parameters in the next layer in an appropriate way. What happens if I multiply not by 5 but by -5? The magic is gone. Why? Because then if I multiply all the coefficients by -5, the output of the linear mapping is multiplied by -5, but this flips the side I was on from being positive to being negative, from being negative to being positive, and then the output is not 5 times bigger than it used to be. Okay? Yes, but I'm not doing it twice here. Okay, so it's only with respect to positive multiplication by positive constants. Next. an overview of the attack. So our attack sequentially recovers the parameters layer after layer in the same way as when we are breaking a crypto system, we first try to attack the first layer. Once we find everything we need to know about the first layer, we can peel it off by translating every input to the original mapping into an input to what remains, because you already know the input. So the intermediate stage of the attack has, suppose that I'm now interested in extracting the ith layer parameters when I already know all the parameters of the first I minus 1. So the input mapping is known. Here I have, this is completely known. Here I have a linear mix, affine mixing, which is unknown. A linear, non-linear ReLU, which is known. And then totally unknown output function, which describes how all the remaining layers from the I plus first until the last one, what is their action on the intermediate value. So I'm now going to concentrate on the intermediate point in the attack, where this is a completely known function, this and this are completely unknown. Any questions about the stage of the attack we are at? Next. So I already said that the inputs are n real values, the DNNs has multiple layers, each consisting of the same number of neurons, and to simplify further, I assume that the number of neurons is smaller than the dimension of the input. And if you are given multiple outputs, actually I don't need them. I can throw away all the output except one output, which I'm going to keep. All the others may simplify the attack, but not actually necessary. It's enough for me to be able to look at n real value inputs, and the output is, for example, the first output, and analyze it very carefully. Now we get into some definitions. A critical point is defined as a point in the input space. The input space is R to the n. I look at a particular point in the input space, and I'm defining it to be a critical point if some ReLU somewhere among all the layers is just having its input being equal to 0. Okay? So if I move around, increasing or decreasing slightly, that ReLU is going to move from its positive to the negative side or vice versa. So this is where the behavior of the network suddenly changes, because some ReLU internally is flipping sides. And this is creating nonlinear behavior. Now, in the vicinity of any non-critical point where no ReLU flips from side to side, in that vicinity I can replace the ReLU just by either the 0 or the identity function, and it will be valid in the whole vicinity. And therefore, the whole network becomes a composition of linear mappings, which is a linear mapping or an affine mapping. Okay? So around non-critical points, I have affine behavior. At critical points, I'm switching from one affine behavior to another affine behavior. If I cross to the other side, ReLU suddenly stopped being a 0, started being identity. So a change of behavior, a very sudden one. Okay, now we are going to look at the input space. Let's assume it's a two-dimensional input space. And I take an input vector x1 and another input vector x2, nothing to do with each other. This could be an image of a cat, and this is going to be an image of a dog, which I downloaded from the internet. What does it mean to go in the input space in a straight line between them? I'm taking for each pixel a linear combination of the value in the first image with the value in the second image. Or more precisely, there is one parameter which I'm going to call t, which describes, it ranges between 0 and 1, and it describes where I am along the straight line. So I'm taking this vector and multiplying it by 1 minus t, and add to it this vector multiplied by t, and as t moves from 0 to 1, my image continuously moves from being the image of the original cat to the image of the target dog. Is it clear what does this traversal mean? Now it's a function from one input variable into one output variable. What is my input variable? T, where I am along the line. What is the output variable? It is what is the output. I told you that it's enough for me to look at one output of the original DNN, and it tells me what is the output while I am at a certain fraction t of my traversal from x1 to x2. Questions? What do you expect will be the shape of this function? This is such a simple function. From one input to one output, I can draw the graph. So it is going to be piecewise linear. It is going to initially, for example, grow. So I started from a point. It's very unlikely to be a critical point. But then I'm reaching a critical point at which some ReLU is switching sides, and suddenly the whole mapping becomes a different linear mapping. And then I again, another ReLU is switching sides, and I have another ReLU. So those points, I'm moving from linear behavior, affine behavior, represented by cell 2, and then move to cell 11, and then 13, and then 8, etc. So going back, my original point was in region 2. While I was walking, I was crossing into linear behavior number 11, and then linear behavior number 13, and then 8, 7, and so on. Each one of them is represented by a straight line, and I can, looking at the output, I can identify the point at which there was a break. And the point at which there was a break gives me a point at which a ReLU was exactly equal to 0. So this is like a side channel attack. It leaks information about some internal point in the cryptosystem, something you usually don't get when you attack cryptography. You get access only to input and output. But in this case, somebody is telling you that this particular point is exactly 0. This particular point is exactly 0 anytime I change direction in the output function. And this is what I'm going to use. And this is an explanation why I needed an activation function which is ReLU or leaky ReLU or anything which is piecewise linear. If the activation function was sigmoid, there will not be any clear breaks where you are changing direction, and therefore I'll not get this leakage of information from inside the deep neural network. Any questions so far? Yes. So what I'm doing, I start from one image of a cat, one image of a dog, arbitrary ones, and I go in a straight line from being a cat to being a dog. So for example, halfway through, when t equals 1/2, it is a mixture. Visually, it's going to look like a mixture of a cat and a dog. Okay. Good. Now consider a critical point x0, which is associated with a ReLU located at exactly the layer I'm now at. Remember, I already solved all the previous layers. Now there is layer number I, which is unknown, and then there are later layers that I'll deal with later. But suppose that the critical point happened due to a ReLU in the current layer switching sides. This will give me a linear equation in terms of all the unknown parameters. Why? Because you know that the input to the ReLU was 0. The input to the ReLU is exactly like the output of the affine function before it. And that affine function, I know that its value is equal to 0, so it's a linear equation. Once I'll get enough linear equations, I'll solve them, and then I'll find all the coefficients of that neuron. There are still missing elements, but that's the big picture. Okay? So, now we have to be a bit careful about, given the location x0, does it survive going through all the later layers, which I don't know anything about? You remember? Here. I'm at this stage. This is known input function, unknown output function. And now I'm asking if there was a ReLU which just flipped from one side to the other. Will its value, the value of the ReLU, be visible somewhere in the output? And how is it going to be affected by the fact that I don't know this output? So my claim is the following. Think about this output. It will have also piecewise linear behavior. Every point is a piecewise linear behavior as I'm moving in the input space. And the value of this piecewise linear is going to be transformed further by the output function. So if it used to be up and down and straight and up, this function is going to break each piece into parts, and it's going to start by going down and then going straight, etc. But, and this is very important, the locations of the breaks are going to be determined only by this and not by this. So I don't have to know G in order to be able to translate from a critical point visible in the output. So its values I ignore, I don't care about the value. But the x coordinate, exactly where the critical point happened, is only due to the fact that up to this point, the input to the ReLU was exactly 0. Nothing that you will do later on is going to affect the location. It will only affect the values of the output. Of course, there could be things which happen with probability 0, namely, there was a break, and this G is also going to be to have another ReLU which breaks at exactly the same point, and it will straighten the line by, it used to be a line like this, and now the output function will exactly straighten it, and the breakpoint will not be visible anymore. But I'm going to ignore 0 probability events. It's very, very unlikely that if I go in my input space in a random direction, I'll be so unlucky as having another ReLU which will change in exactly the same location. Okay, so now that you know that if I see a break in the output, the very last output layer, the location of the break is only determined by the input function, which I know, and the unknown affine mapping, which is in the one layer. I know that it is going to map something to 0. And this will give me the linear equation, or affine equation that I need. Questions, this is crucial. You have to think a little bit about it to convince yourself that you don't have to know anything about the output function, and this is very lucky, because otherwise I wouldn't be able to solve layer by layer and extract all the weights. Okay. So we were here, so now we are here. Another definition. The signature of a neuron is defined as the normalized vector of coefficients. I told you already that I have no chance of finding the real set of coefficients because I could multiply it by 5, I could multiply it by 0.1, I could multiply it by 1,000. All of them could be used to have exactly the same input-output behavior, provided that the next layer I'll compensate for what I've done by multiplying by a positive constant. So the best I can hope for is to have a normalized vector where you divide everything by C1. I'm going to assume that C1 is non-zero. I'm again making simplifying assumptions. If C1 was 0, I'll divide by another Ci. So let's assume that this was a 1, and this is going to give you the ratio of C2 divided by C1 up to the bias divided by C1. This is kind of normalized definition of the neuron, and that's the best I can hope for. I cannot find whether this is 1 or this is 5. But I may have missed one important thing. If C1, for example, was negative, you see, if I take the whole equation and multiply it by -1, then the signature is going to remain the same, because I look only at ratios between pairs of values, and if all the values are multiplied by -1, the ratios between pairs of values remain the same. But for the ReLU, it's very important to know if it was 1 or it was -1. And this is lost when I do the normalization. In other words, once I find the normalized form, which I call the signature, there is one change which I can easily do, and this is multiply this vector by 5 or 7 or million, any positive constant, and I'll just pick any value I want, and it will be compensated for in the next layer. In the next layer, my equations are going to be automatically going to give me values which are divided by this constant. But I don't know if the signature represents the real vector, or I should add a -1 to it, namely this will become -1, this will become minus C2 over C1, etc., because this transformation, multiplying the whole signature by -1, totally changes the behavior of the network, because the ReLU is switching from positive to negative and behaves differently. So there are things which are unimportant, like which positive constant I multiply by. I don't care about it, but it's going to be very problematic for me, and that's one of the main reasons why Carlini et al. In Crypto 2020 couldn't get a polynomial time algorithm, because they couldn't determine for each neuron whether it's on the positive side or the negative side, and I'm going to show you, among other things, how to do it. Good. Questions so far? Now we have the signature, and I'm going to show you how to find the signature. Okay. So I already said that you can multiply it by positive constant, that's okay, but the signs might be flipped, and then it's very important to know if they are flipped. How do I find the signature? These are the ratios between any two coefficients. Very easy. Suppose that I'm at a critical point. So x0 is a critical point in the input space. I walk in the direction of the first coordinate of that neuron, a very short distance epsilon. I'm moving away from criticality. The red line describes the critical points for the current neuron, which locally looks like a straight line. You know, it is going to be affected by other neurons flipping sides, but I assume that very locally, only this neuron is flipping when I go from one side to the other side. So I leave criticality. I start with a criticality. I know that it's critical point because there was a bend in the output function. I leave criticality by going in direction first coordinate, and after going a short distance, I'm trying to return to criticality by moving in this direction, the input space, until again I see a change of direction, which means that I again hit criticality, and the ratio between this size and this size is going to give me the ratio between the two coefficients. Is it clear? I'm hiding under the rug all kinds of complications, but that's the basic idea, how I find ratios between coefficients of moving out of criticality and then back to criticality. And just like you know that the slope is determined by the ratio of this distance from this distance. Okay, next. All this was under the assumption that the critical point was in the current layer that I'm interested in. But maybe the criticality happened due to earlier neurons, or maybe it was due to criticality in later neurons. I have to determine them. Then the answer is very easy. If the critical neuron, the one that flipped, happened to be in the earlier layers, I know everything about the earlier layers. So I could calculate the values there of all the neurons, and I would see that one neuron is exactly outputting 0 now at the point of criticality. So because I know everything about the input function, I can determine if the change of direction is due to a neuron that I already know and recognize from earlier layers. However, I still have to distinguish whether it is in the current layer, I still don't know anything about it, or future layers. And here we use a simple trick. What would happen if I do all this analysis, when the neuron was in the future, in a layer which is not the current ith layer? Then what is going to happen is that the input function, which determines how inputs are translated into inputs to the neuron, I'm wrong about it because I assumed that it was in the ith layer and that I knew how inputs are translated to its inputs, to the inputs of this neuron. But if the neuron that flipped was later on, my whole assumption is wrong. The mapping from input behavior to the inputs of that neuron looks totally different. Therefore, I'll get a signature, but it's a wrong signature. It's not associated with a real neuron. So if I explore a large number of traversals, so I don't take only 2 points, cat and dog, but many different points, I connect them in pairs, and each one of them is going to go through many, many changes of direction. For each one, I calculate the signature, and now I throw away all the signatures that I already saw this signature. I know that this belongs to an earlier one. Among those that I don't recognize, if the signature occurred only once, it's likely to be at a later round, at a later layer, because every time I'm using the wrong calculation of how inputs are translated into that neuron's input, and therefore each one of them is accidental signature. But if it is in the current layer and the mapping from inputs to input of that neuron is correct, I'll see several times the same signature. And that's my test, how to know if a signature corresponds to a neuron in the current layer. Any questions about this?
Is there a holistic analysis of like the success rate of this behavior?
This is, when you talk about infinitely precise numbers, the chance that 2 random vectors are going to be identical in R to the n, 2 random points in R to the n are going to be the same, the probability is 0. So that's why I'm not using finite precision, because then I'll have to go through a very careful analysis of errors and propagation and their effect. But with infinitely precise coefficients, which are, I assume are random numbers, I'm unlikely to see the same signature occurring twice, exactly the same occurring twice. Okay. So now we've solved most of the problems. So here I explain why it is likely to identify the correct layer. So while I'm doing my traversals, I'm keeping all those bands, but I concentrate only on those bands which are in the current layer. And I hope that after I do enough experiments, I'll identify the signatures of all the neurons. And this answers the question I was asked earlier, I think by you, whether I need the architecture. If I need the architecture and I know that there were 1,000 neurons, after I see 1,000 signatures occurring, each one occurring multiple times, I stop. If I don't, it's a coupon collector problem. So I keep collecting more and more and more until for a long time I haven't seen any new signature occurring. And then I say I know all the neurons in this layer. So that's why I don't really need the architecture. Next. So the problem now that I'm going to consider, and this is likely to be the last idea of the whole algorithm, is how to find the coefficient, whether my signature is the real one or it has to be multiplied by -1 in order to be the real one. When I look only at ratios of coefficients, I lost this information. So basically it's to tell whether my traversal moved from the negative side to the positive side or from the positive side of the neuron to the negative side of the neuron. From looking at the output, neither one of them by itself is going to be flat. So the output is going to look like going down and then going up, or going down and then going down even steeper. It doesn't tell me whether I'm on the going from positive side to negative side or negative side to positive side of the neuron. Okay. Now, look at the deep neural network. This is the current layer. And I would like to use what we call a wiggling technique. And this is an idea that comes from differential cryptanalysis. In differential cryptanalysis of block ciphers, I'm trying to change the input by XORing to it a particular change vector, and I'm choosing in which direction to change the input so as to maximize a certain property which exists in the block cipher. So if you're not experts in block cipher cryptanalysis, forget what I just said, but the idea is I have a vector in R to the n, and I want to change it, but in which direction I change it will be determined by what I try to achieve. I can move it in all possible directions in R to the n, but my goal is to change it in such a way, so I'm think about this vector being wiggled in this direction. I'm going back and forth short distance, and I want this neuron to wiggle a lot, and all the other neurons to wiggle very little, to be almost unaffected by the changes in my input. So the question is, in which direction do you want to do it? So if it was a neuron in the first layer that I directly control the inputs, then if the vector of coefficients is in this direction, pointing in this direction, and I can change my input, which is multiplied by this vector of coefficients any way I want, how will you get the maximal possible dot product between this direction and the direction of change? It is determined by the dot product between the direction of the coefficient and the vector of the changes. If the vector of changes is perpendicular to the vector of coefficients, then moving in the perpendicular space is not going to change the output at all. If I'm moving in the same direction as the vector of coefficients, then the effect on the output is going to be maximized. So if my goal is to take a vector which is in this direction and to wiggle by a small change of size epsilon, but I'm allowed to choose the direction of the wiggle any way I want, choose the direction which is the same direction as the vector of coefficients, and then you'll get the maximal possible change. What happened in high dimensional spaces? Random vectors tend to be, with high probability, almost perpendicular to each other. Okay? Think about two unit vectors pointing in random directions. The dot product between them is going to be almost zero because you are going to have to add and subtract roughly the same amount. So I'm going to wiggle the input in a way that after going through the known input function, the inputs to that neuron are going to be in the direction of its coefficients. Now the coefficients are known, but I don't know if it's positive or negative. So the vector of coefficients was either this one or its opposite in that one. But it doesn't matter for the wiggling. I'll get maximal wiggling. If I know the vector of coefficients up to sign, without the sign, I'll just wiggle in that direction. So I'm wiggling the input so that after the transformation by the known input function, the change in the input to this neuron are going to be exactly in the direction of its known coefficients, but I might be going in the opposite direction, doesn't matter. I'm interested only in the size of the wiggle. So I can create a situation in which this wiggles very strongly as a reaction. What happens to other neurons? Again, under some randomness assumption and that it's high dimensional vectors, the effect on the input is going to be totally uncorrelated with the direction of the coefficients, and therefore the dot product between them is going to be very small, and therefore the other neurons are going to wiggle very, very weakly, but this neuron that I prepared the wiggle for is going to go strongly back and forth. Okay? Now, the next thing you have to think about is, I want to know whether I'm going from positive to negative or negative to positive. Now, if I am in the positive side, the linear mapping, which wiggle the output strongly, is going to pass through the ReLU, because the ReLU is in the positive side and it is copying whatever wiggle you had in the input to the output. If the ReLU was on the negative side, the input to the ReLU might wiggle a lot around -5, but the ReLU is going to block the changes. I was wiggling, I was around the point -5. I wiggle between -4 and -6. Doesn't matter. If the output of the linear combination changed between -4 and -6, after the ReLU, you get 0, no wiggling at all. And therefore, in one situation, everything wiggles weakly, including this one being 0 if I was on the negative side, and if I was on the positive side, I have a strong wiggle going through, and this is going to be visible by the output, whether it changes strongly or changes weakly. Let's finish with the examples. Let's skip the analysis of the sizes of the wiggles. So basically, a single wiggle is weak evidence. It's not enough because you might be unlucky, you might just be going in the direction of another neuron. But here is one occurrence, one point in the input space where a particular ReLU switched, and due to the input function being different in this part of space and in this part of space, here the ReLU switches when you cross this black line. So this is one side of the ReLU and this is the other side. And this is another point in input space where the same ReLU with the same signature is switching. And again, think about the green being the side where I keep the signature as is. I don't multiply it by -1. It is 1 followed by C2 divided by C1, etc. The red side is when I decide to flip the value of the signature, and I say that the real coefficients are -1 and then minus of the others. So now I have many votes, and I have to see whether the wiggling when I move in the green direction on average is stronger than the wiggling on the red or vice versa. And I can do multiple experiments, and I expect the correct side to win eventually, and I'll show you the results, and this will be the end. So we always ran 200 experiments. This is in order to solve the 1.2 million parameter problem with 8 layers, 256 neurons per layer. So among the real sign of the first neuron was minus. I had to flip the signature by replacing the 1 by -1, and similarly for other coefficients. So the real sign was minus. 165 out of the 200 experiments voted that the minus is where the wiggling was stronger. 35 voted that the wiggling on the wrong side was stronger, but clearly the decision is favoring the correct one. The second neuron is even more extreme. In this case, the real sign was plus. 0 cases out of 200 voted for the minus, and 200 voted for plus. Third one, the real sign was minus, 198 voted for minus, 2 voted for plus. Basically, after 200 experiments, you never saw a wrong conclusion about the sign of the neuron. And that's it. I told you all the elements of the attack. So in this talk, I showed that you can ask polynomial number of queries and analyze the answers in a polynomial amount of time, and with very high probability, and the probability is over the votes, you just have to choose a sufficiently large number of tests, but it's all polynomial, you can find all the parameters. And we demonstrated the practical applicability by solving in 30 minutes the problem that would have required 2 to the 256 time using the best previous algorithm. Thank you very much.
Thanks to Professor Shamir give us very good, very informative talk and give a new approach to attack the DNN models. So in the mornings, Professor Yao told us he don't worry about his work. So now I can tell you I don't worry about work. So I can do something like this. So, and the questions? Oh, okay.
Okay, so about the smoothness parameter, I'm assuming that all the vectors of coefficients are not much larger than a unit vector. So their size doesn't increase to infinity. So they may have, size 10 or size 3, but I'm not assuming that they have size billion. So that's an assumption about how the parameters are divided. And when you make this assumption, for 8 layers, you needed a precision of 64-bit. Everything we did in the demonstration attack was using 64-bit accuracy. How does the number of bits increase with the layers? For every additional layer, you have to add a constant number of bits to the accuracy. And because running time, if I measure bit complexity of multiplication, it goes like n squared, where n is the number of bits. So if every additional layer requires only increasing by a constant number of bits, the accuracy, even the bit complexity is going to be polynomial. So this is the smoothness assumption. Yes. Yes. If I'm using 64-bit accuracy, I mean all inputs can be moved by 2 to the minus 64 or any multiple of 2 to the minus 64, and all my arithmetic operations are done by adding or multiplying 64 bits. So I'm actually working in a discrete space, but with 64-bit accuracy for everything, the inputs, the parameters, the biases, etc. If you have enough bits of accuracy. Just to simplify the analysis, I showed here the case in which you have infinite precision, and therefore I don't have to worry about these issues. Okay.
There's a bit of technical detail in the sign determination product that I don't understand. So you argue that in n-dimensional space, the dot product between two random vectors should be very small. In principle, the square of this dot product should have average 1 over n. So the dot product should
is 1 over square root n?
Yeah, 1 over square root.
But this is what I call very small. N is large.
You skip that, right?
Yes, this is the analysis which I ran out of time for here. So basically, each entry in the dot product, one vector I assume is unit vector, and the other one is an unit vector multiplied by epsilon, a small amount, that's the wiggle. So each entry by itself is approximately epsilon over square root d. And then here you have one of two possibilities. Either this is the full epsilon, which is what you are going to get when this neuron is on the positive side of the ReLU. So the full epsilon is going to be visible in the output. And the other possibility is if the changes in this of the outputs was on the negative side, then you get roughly the same thing for other neurons. But the neuron that I'm now looking at, trying to attack, the one I'm trying to wiggle strongly, is actually going to give you a change of 0. And then I'm analyzing what is the norm of the two vectors. And the norm of the change vector, in one case, it's about 0.7 epsilon, and the other case, it was, where is it? 1.2 epsilon. So the ratio between the two wiggles is almost 1 to 2. So I'm trying to distinguish between two numbers, each one being randomly distributed. When one of them is around 0.7 epsilon, the other one is around 1.2 epsilon. But we have to shorten because people are leaving now. No time. We have to switch to another talk. Thank you.
Thank you.